let's recall where we were. I'll do a little review. We're using the bracket polynomial in this form, where the variable is q, and we will evaluate the loop as q plus q inverse, and even the unknotted circle gets an evaluation in this form, and we expand with a minus q here, and then we can check. I just remind you what happens. We might come back to this if we wanted to calculate something, that under a positive curl, you get a q inverse, and under a negative curl, you get a minus q squared. And under a second Reidemeister move, you multiply by minus q, and it's invariant under the third Reidemeister move. This reflects how the grading will change when we go to homology, you see, because we will be looking at a chain complex whose q, the j is going to be shifted, you see, in this way. So we have to keep track of that, but I won't worry about that at the moment. I'll just be thinking about the homology, and then we'll do the grading carefully next time. But these calculations are worth checking, and also that you can normalize it in this fashion where n plus and minus are the number of positive and negative crossings in the diagram. And then we talked about how to do enhanced states and label them with x and 1 instead of minus 1 and 1. And the bracket then is the sum over the enhanced states, the ones with the plus or minus 1s in them, of minus 1 to the number of b's in the state, and q to j, where j is the number of b's plus the sum of pluses and minuses from the loops. And that we could rewrite this by saying, well, it's just the sum over all the i's and j's that are possible times the number of states that have that particular I and j, which we are writing as the dimension of a module, where the module is the ones that are generated by those states. And as we've seen, those states can be regarded as the generators of the chain complex. And then we defined a boundary mapping which took the number of b's up by 1, but it leaves the j alone. And by using that criterion, we discovered the Frobenius algebra. And so we ended up with a chain complex, and we have that the graded Euler characteristic of that chain complex gives rise to the bracket, gives rise to the Jones polynomial after a normalization. And I remind you how it works, in that if you think of the states as collected up in such a fashion, then the ones with no b's go to the ones with 1 b, and we take the direct sum of these. But we could, for the sake of thinking about it, just draw out a category like this and remind ourselves that we are supposed to be taking the direct sum of this module, and that module, and on down the line, 2 b's, 3 b's, to get the chain complex as the direct sum of these, the direct sum of these, and so on. And that the boundary mapping takes an alternating sign pattern from the way the A's have been turned into B's. If you turn an A into a B and it's preceded by an odd number of A's, you put in a minus sign. If it's preceded by an even number of A's, you put no minus sign. So it goes like this. And that leaves you with a little formal exercise to check that this formal way of taking a boundary by removing A's and B's from a kind of cubical simplex like this works, that boundary equals 0. And then to preserve the j while raising the I by 1 means that the total of the sign sum on the loops has to go down by 1. And in order for the sign sum to go down by 1, we find that indeed, I'll just go to the algebra, that the boundary should behave like this. For example, here is a minus 1, And when we went to this tensor product, we got a -2. And here, when we went to this tensor product, we go from a 1 to a 0, x and 1 adding up to 0. And so we get these for the co-boundary, for the co-product part of the boundary. And similarly, in the multiplication, we have x times x is 0 in order to not have to worry about going down too far, and that x times 1 is x, and x times 1 is x, and 1 times x is x, making sure that this goes from lambda equals 0 to lambda equals -1. So we end up summarizing the boundary structure in this little algebra, z of x mod x squared, with this coproduct structure. And that's a nice way to keep it in mind. And then we checked order compatibility in the sense that if you did the local boundary on an A smoothing first and then on another A smoothing after that, you get the same result as the other way around. And that when you do that, the corresponding little cobordisms that you draw, multiplication being going through a saddle from 2 circles to 1, and co-multiplication being going from 1 circle to 2, those surfaces that you produce are homeomorphic. So the algebra, the Frobenius algebra that we wrote down, is knowing about the cobordisms of surfaces. It's compatible with them. It's a small topological quantum field theory in the terminology of that subject. And we can do exercises, and you should do a few more than I did just to see that it does work. So we have the boundary structure for the complex, and then we added some extra information in order to be able to handle this way of thinking. And the extra information we added was the unit and the co-unit, namely going through a bit of surface that starts from the ground ring and goes into the module. That's the unit, and takes a 1-to-1, or the co-unit, which has to be determined, which will take an element in the ring and apply epsilon to it and make it in the ground ring. And what should that be? Well, we want to follow the principle that homeomorphic cobordisms will give you the same result. So a tube is just an identity map. And if you put a little handle in here like this, by going through a saddle and then through a minimum, then you find that when you got to here, you did delta of A. We might look at it abstractly to see how it looks as well. Delta of A would be some sum of tensor products. And then we would apply epsilon, which would mean that we would have epsilon of the first product term, and then we would multiply these and add them. And so in the case that we're concerned with, if we were to put in 1, then we will be looking at epsilon of 1 tensor x plus epsilon of x tensor 1, and multiplying it, and we get epsilon of 1 times x plus epsilon of x times 1 equals 1. And so we need that epsilon of 1 should be 0 and epsilon of x should be 1. And knowing that, we now have the full topological invariance for these cobordisms. You can draw anything you like, and it's a nice experiment for you to try, or try proving the whole theorem about it. That if you have two homeomorphic cobordisms of circles, then the maps that you get from them will be the same algebraically. And we pointed out that if you have a sphere, then you go from 1 to 1, and then you take epsilon of 1, but epsilon of 1 is 0. So that means that a sphere's evaluation is 0, but a torus's evaluation is 2. And a higher genus surface evaluation is 0. And with that, we can look at some examples. And I want to remind you how we examined the invariance under the second Reidemeister move. So what we're going to do is think about the chain comparing the two chain complexes. And one is simply locally just this, but this blows up inside the larger diagrams of the larger chain complex into this when you have the Reidemeister move, because you have these different smoothings. And we wanted to show that the two obvious mappings that will carry the lower complex to the upper and the upper to the lower, those two mappings are, when you compose them in either direction, chain homotopic to the identity. And so we went through this, and I'm just going to go through it again because it's interesting and it bears looking at again, but I'll go through it quickly and you can look at the slides which are in the show, which are in the Dropbox. But what we discovered was that we didn't have to worry about the top line because the top line is almost the same as the bottom line here. What we had to worry about was the back and forth maps along the bottom line here. And the back and forth map that goes from here and back to here is the composition of first do F1 and then do G1. And F1 gives rise to a circle and goes through a saddle. And G1 lets a circle die and goes through a saddle. So that F1 gives rise to F1 goes through a saddle and gives rise to a circle. And G1 lets a circle die and goes through a saddle. And if you did F1 and then G1, then you would have this, and you would have a little sphere in the middle, but that makes that map 0. So that in going from here and back, you get the 0 map on the lower part, whereas on the upper part, it's the identity. And so when you go this way into the more complicated complex and back down, you get 0 on one of these maps, and you just get the identity on the other end. So there's nothing to worry about. On the other hand, if you were to start here, go through G1 and come back on F1, you have a non-trivial mapping on the lower part of this complex. And that's the part that we wanted to analyze. And we wanted to analyze it and show that it, that is this one, is chain homotopic to the identity. And chain homotopic to the identity could be accomplished if we had a map that went this way and another map that went this way, so that if we were to take this and then take the boundary plus this and then take the boundary, both going back into here, that should essentially be equal to the identity minus this map we're thinking about. And we can draw pictures of everything. We can try for the simplest map that will go back this way. And the simplest map that goes back this way is giving birth to a circle. And the simplest map that goes from here to here is letting a circle die. And so we have the following situations here. We have the F1 map, the G1 map, the boundary maps, which depending on which way they go, give birth to circles or have circles die, but the circles go through saddles and get connected in. And then we have the H1, which was going to, here's our little bit of complex. The H1 wants to have a circle die, and it does. No saddle. And the H2 wants to have a circle born, no saddle. All right. And the other ones, the boundaries, let's look at them again. Boundary 1 is to do a boundary here at A, turning it into a B. And if you look up the picture of boundary 1, you see that, that what happens is that you go through a saddle and give rise to this circle. And that's what happens when you do this. You go through a saddle and give rise to a circle. And when you do the boundary 2 over here, then you're going to amalgamate this A, so it goes through a saddle and amalgamates here. So you have the boundary 1 and boundary 2 maps also described geometrically, and we don't have to have any algebra here except the essential algebra of the maps. And now we want to look at what the formula would be for a chain homotopy. And so we write it down, and the formula, as I said, is first do H1, then do boundary 1. First do boundary 2 and then do H2, and then you have these two things, which I should add up to the difference or the sum mod 2 of the result of doing G1 and then F1. And what does G1 F1 look like? G1 F1 means you do this and then you do that. So these are meeting along the middle, and it means you go through a saddle and then you go back through a saddle. And at the top, you have a circle born and you have a circle die at the bottom. So you have the G1 F1 here, where these met along the middle, producing a tube between these two bits of surface. And in the identity, it's just a tube going down from top to bottom. That's the identity on this thing here. And then the H1 boundary 1 and the boundary 2 H2 are things like this. And then there's a pattern to this, a remarkable pattern, which is that if you think of 4 bits of, I'll go to the next page and remind you there, you have 4 bits of surface, and for those 4 bits of surface, each one of these blocks that we wanted to add up to 0 or add up to the other 2, they are each of the form, take a tube and put it between 2 of the bits of surface, 1 and 2 here, 3 and 4 here, 1 and 4 here, and 2 and 4, 2 and 3 here. So the pattern is essentially 1, 2, minus 2, 3, plus 3, 4, minus 1, 4, meaning the tubings between the bits of surface should be equal to 0. So, so this is Dror's observation that if you started with thinking of nothing but the cobordisms themselves, you didn't have any algebra, then you would get the essential thing that you need for the invariance by factoring the cobordism theory by this relation, which he calls the 4-tube relation. So that means that if we had been abstract enough, we could have said this whole theory without any of the Frobenius algebra at all, but then we wouldn't have connected down to the Jones polynomial so easily. But we would say that we consider the category, we think of it additively so that we can form an analog chain complex, and we mod out by these cobordisms, and then we would get invariance under the second Reidemeister move. I promised to go through the other Reidemeister invariances, but I decided that I would have a technical talk about that and other matters next time. So you can think about what happens to the other Reidemeister moves yourself. That's another exercise. For example, go and think about the first Reidemeister move. That's going to be reasonable, right? That's small. And then how are you going to think about the third Reidemeister move? There's a puzzle, right? Can you somehow keep it simple, or is it going to get much more complicated? Well, you can keep it simple. And if you would look at Jor's papers, you'll see how he does that, or you can try to do it yourself. And we'll come back to that whole thing. But the main thing about the invariance is the 4-tube relation. And then the nice thing about the 4-tube relation is that you can play around with it and reformulate it into some ways that show how it docks perfectly with the Frobenius algebra. So I want to review that a little bit too. So one useful way of dealing with this situation is to use a symbolism where I have a little line meaning a little bit of surface. And maybe a little wiggly line between them means a tube between them, and then I can sketch a pattern without drawing the whole thing out. Yeah. So then the 4-tube relation in schematic form looks like this: 4 bits of surface, 1, 2, 3, and 4, and you connect 1 and 2, or you connect 3 and 4, you connect 2 and 3, or connect 1 and 4, like that. And then you can look at different aspects of that. And one aspect that we talked about last time, and I won't go walking you through the whole detail of it, is that you can show that the 4-tube relation implies that a single tube is the same as a little circle that cobords a torus, and then a disk cobording. and then plus a disk cobording and a bit of torus. But you remember from our algebra that going through the torus, maybe you should remember that a little bit. Let's go back to the torus and see what it is I'm saying. Well, torus was way back here. But if you go through a torus only up to here and you don't go all the way to the end, just up to the little circle. So that's a little circle bounding a torus. And you watch what the evaluation would be. Then you see you start with a 1 and you have a 1. And then you have 1 tensor x plus x tensor 1. And then you multiply out and you get 2x. So it's 2 times x. So that means, and you could think of it the other way and it would be the same. So it means that that when you have a little circle and a torus underneath it, then that's as good as having the algebra element 2x labeling a little thing without a torus. Algebraically, it's the same as having 2x, x, and then I'm divided by 2, so x. So we know that, so symbolically, we will just put a little blob, thinking of it as an algebra blob that represents this bit of torus. And so now we have a nice cutting a tube relation, which says that if you have a tube, you can break it this way and that way and add them up. And we can try to connect with some unknown algebra by calling that x and seeing what kind of an algebra we would get. And then I also pointed out to you that if you had a relation of this kind, it would imply the 4-tubing relation by expanding it out and watching the signs in the expansion, and it all cancels things out correctly. So this all bears thinking about more carefully, but we're going to use it formally now and see how it relates to things. I won't go through that part, but I will go through this part again. This was how we can get to a Frobenius algebra from the tubing relation. So as I said, you could imagine that we went through all this reasoning without the algebra, and then we're looking for an algebra. And so we say, well, I want the algebra to satisfy this, so let's find out what it says. And we can write down the algebra translation of this. And the algebra translation of this is the tube on the left is the identity map. So if we had an alpha going in, we'd have an alpha going out. But here, alpha gets multiplied by x and has epsilon applied to it. And then it gets multiplied by 1. And over here, alpha just gets epsilon applied to it, and then it gets multiplied by x. So you see, the tube relation translates directly into the algebra formula that any element alpha in the algebra should have the property that it is decomposed in terms of 1 and x in the algebra and coefficients. So then we can put in x and find out some relations. And we did this last time, and I'll just go through it again. X, if I put in alpha equals x, then I get epsilon of x squared times 1 plus epsilon of x times x. And that tells me that epsilon of x should be 1, and epsilon of x squared should be 0. And then I put in 1 for alpha, and I get 1 is equal to epsilon of x times 1 plus epsilon of 1 times x, and that tells me that I should have that epsilon of x is 1. But I already figured that out, and it tells me that epsilon of 1 is 0. So I know all these things, and then I wonder about the powers of x, because I haven't prejudiced my algebra yet. And I find that x squared, by the same formula, will be epsilon of x cubed plus epsilon of x squared x. And that tells me that x squared is going to be a multiple of 1, because epsilon of x squared we figured out was 0 already. So x squared is a constant. And now you see if we had gone through all that reasoning, we could then have said, well, then, excuse me, I'm just going to go over to here. Here's the most general algebra. Once you figure out the coproducts, which goes by a similar method, here's the general algebra, and then what will fit with the polynomial? Could we make this algebra work in such a way that the j is fixed? And then we realize that what we did before fits into this perfectly. And in order for the j to remain fixed, we need the k equal to 0. If the k is not equal to 0, then the j will not be fixed under the differential, and we won't get such a neat formula prefiguring the bracket or the Jones polynomial in terms of the homology theory. But we'll still have homology theories. And so the two basic homology theories that have been studied here in relation to this algebra have been k equals 0, the Khovanov one, and k equals 1, the Lie one. And we will come back to the Lie algebra and other things as we go along. But for right now, I want to do an example. So let's switch to the Blackboard. So we could do more calculation, and I thought for next time I would have some well-prepared calculations for you to look at. But for now, let's just do one or two that are easy, just to see how things work out. So suppose we take the Hopf link. Call it H. And let's write down the picture of the Khovanov complex for that. So the A-type smoothings are these two. And then we can smooth the top one. Or we can smooth the bottom one. Or we can smooth both of them. So this is I equals 0, no, all A's. This is I equals 1, and this is I equals 2. And if we were computing the j, then the j will be equal to 0 plus lambda, where lambda is plus, 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 minus, minus, plus, minus, minus, right? And the j here is 1 plus lambda, and the j here is 2 plus lambda. And now let's actually display everything that could happen. So I will make a list here of the values of I and the values of j. The values of I are 0, 1, and 2. And now you'll see when we do the calculation that I only need even values in this case. So I'm going to have a -2, and then I'm going to have 0, and then I'm going to have 2, and then I'm going to have 4. You'll see when we do it that that's all I need in this case. So let's put in the corresponding algebra element. So for I equals 0, we're working entirely here. And we say to ourselves, well, what will give us -2? And the answer is x tensor x, right? Labeling both of these with x, labeling them both with -1. Now, what will give us, what happens next? We have xx, but to go up a little bit in lambda, you could have x and 1 or 1 and x. And those x and 1, where x is -1, 1 is 1, gives you 0 for lambda. So we'll be in 0. And this will be x tensor 1 and also 1 tensor x. I'm just making a list of the terms, list of the generators there. Now for 2, we're still working here. This is I equals 0. For 2, we could have 1 and 1, and that's all we have. So we have 1 tensor 1. And for 4, nothing, and I won't write anything. Okay, so this is a picture of the module for this with the gradings, the J gradings. Okay, now we go over here to I equals 1, and we ask the same question. What's the lowest it can be? Well, it's going to be 1 plus the lowest possible lambda. And how low can the lambdas be in each one of these summands? -1 is the lowest it can be. And then we're going to have a 1 added in. So that makes it 0. So it starts at 0. And those are x, comma 0 in the direct sum and 0, comma x in the direct sum, right? You have the direct sum of this module and this module, and I write that as x, comma 0, meaning this plus 0 in this one, and 0 plus x in this one. And those are the ones that have grading, have lambda grading -1 and j grading 0. Now we want to go up 1, and we can only go up to x. And oh, well, we can have one of these x. Yeah, I'm going to write in one summand at a time. So this could be x. And then this one is, I'm sorry, this could be 1. We already did the x. This could be 1. And then 1 and 1 is 2. So you see we'll be in 2. And those two are 1, 0 and 0, 1. So that's 1, 0 here and 0, 1 here. And those have grading 2. And there is no higher grading here. Nothing higher can happen there. So now we go to j equals 2. And we have 2 circles. And what's the lowest you can go? Well, you can have a -1 and a -1. You have x, x. You have x, x. That's giving you a -2. But you're adding 2. So it's going to start at 0 with an x tensor x here. What's next? Well, you could boost one of these to a 1, and then you would have -1 and 2, which gives you 1. So you can be here with x tensor 1 and 1 tensor x. You can have x tensor 1, and you can have 1 tensor x. Okay, and then you can boost an x to a 1, and then you'll be up at 2 plus 2 is 4, and that will be 1 tensor 1 here. So you see, that's why I only needed the even ones. And now I have labeled all the generators of the different parts of the chain complex. If you now have at 0 a homology for this column, you have a homology for this column, you have a homology for this column, and so on. And we can check before looking at boundary operators, we can check the Euler characteristic at the chain complex level, which should come out equal to the bracket polynomial. So let's do a little calculation. What about the bracket of H? Now, the bracket of H, according to our formula for it, is equal to, let's smooth it right there, is equal to the bracket of the A smoothing bracket, that's this one, minus Q times the B smoothing part. And now I'm going to use my shortcuts. This is a positive curl. And so that gave me a Q inverse and then times the value of the loop. And then the other one is minus Q, and this is a negative curl. And so it gives me a minus Q squared times the value of the loop. And so that gives me altogether Q inverse plus Q cubed times the value of the loop. The value of the loop is Q plus Q inverse, right? So that's Q inverse plus Q cubed times Q plus Q inverse. And you can multiply that out and you will get, I claim, 1 plus Q to the fourth plus Q to the minus 2 plus Q squared. Let's stop and check that. Q inverse times Q is 1. Q inverse times Q inverse is Q to the minus 2. Q cubed times Q is Q to the fourth, and Q cubed times Q inverse is Q squared. There we go. Okay, so that's the value of that. Now, on the other hand, we should get that the value of this is equal to the sum on I and j of minus 1 to the I times Q to the j, right? That's our monomial expansion formula for the bracket. So that means that I can go along here and add up the contributions that these would give with a plus, and add up the contributions that these would give with a minus, and add up the contributions that these would give with a plus, and see whether that all adds up to the same thing that we just did. So let's see if it does. So on the first row, I'm going to have plus times. Now, what do we get here? Q to the minus 2, right? Q to the j. That's Q to the minus 2 once. Actually, you only have to see how many occupants there are. Here, there are 2 of them. So we get 2Q to the 0, which is plus 2. And here we get Q squared once. Okay. Then we get minus, and then we get 2Q to the 0, so that's a 2. And we get Q squared twice, so that's 2Q squared. And then finally, we get 1 Q to the 0, 2Q squared, and Q to the fourth. And if you add all this up, let's see what happens. Let me use a color so I can cancel with the color. I have a Q squared. I have a 2Q squared and a minus 2Q squared, so these will cancel. I have a 2 and a minus 2, so these will cancel. And so I am left with Q to the minus 2 plus Q squared plus 1 plus Q to the fourth. Q to the minus 2 plus Q squared plus 1 plus Q to the fourth. So check. That works. Okay. So you see that now you can see how this works and how, in fact, if you wanted to investigate, even without homology, the status of the way the states are contributing to different pieces of states are contributing to the polynomial, you can examine it by writing out the states and then dividing them up into the enhanced states and making a chart of this kind to count what the different contributions are. Now, to look at the boundary maps, I didn't check this beforehand, so I might be a little slow on this, but probably worth our while to look at how the boundaries are working, right? So, so let's do a little calculating. Well, the boundaries, by the way, are going down, right? The boundaries take you from I to I plus 1. So all the boundary maps go this way, and they go down the little columns. So having arranged it this way, we can look at the boundary maps in a way that doesn't get us too confused. So, for example, what is the boundary of x tensor x? Well, you've got to go back up and take a look at where you were. You were here. And there are two ways to go. You have x tensor x here. Like, let me draw a picture of it over here so you can see. And I'm not sure I want to do the whole thing. You can do it yourself easily and then think of it as homework. And then we can check your homework next time. And that's probably a better thing to do than me go through everything. But let's go through a little. So here is x tensor x, right? And when we take the boundary, we're going to we have an A smoothing and we have an A smoothing. And we're going to go to a B and an A plus an A and a B, right? And this one is going to go with a plus because you took the first A. And this one is going to go with a minus because you took the second A. And there are two boundary pieces. And when you multiply, but I'm belaboring a point because these are products and x times x is 0. So in fact, the boundary of x tensor x is 0 plus 0 is 0. And so there isn't anything to do, but I was reminding you of what the rules are. So this goes to 0 under boundary. So that tells you something. That tells you that the zeroth homology at this point is Z, because you have somebody that goes to 0 and comes from nobody. So we found a bit of the homology. Now, what about a next one? What is the boundary of x tensor 1 and 1 tensor x? Well, now I'm going to be using our work, because let's look at the boundary of each of those. The boundary of x tensor 1. Well, the boundary of x tensor 1 means this one is labeled x and this one is labeled 1. And we're going to first do a multiplication here, and that'll give us an x comma 0. And then we're going to take the multiplication in the other one, and that's going to be minus 0 comma x. And that's because of the boundary AA is equal to BA minus AB formula. And so we get that the boundary of x tensor 1 is equal to x comma minus x, if you want to put it into the direct sum that way. And what about the boundary of the other one, the boundary of 1 tensor x? Well, you see, it's the same because you multiply, and so you're going to get x comma 0 minus 0 comma x, which is going to be equal to x comma minus x. So those two have the same boundary. But that means that their difference will have boundary 0, and so there's a cycle up in there. And so it goes. We can continue, and I will write 3 dots, do this homology as an exercise. Okay. So, so I hope I've convinced you that this schema is actually an interesting schema to use, whether or not you were going to be investigating the homology. You could do the homology, but you could also use it as a way to understand what the different state contributions are to the bracket expansion of a given link. And so you could examine it for an example. And then I have an example that I think would be an interesting homework exercise further, but a more complicated one. The one we, oops, excuse me, I want to make sure we save that, so we'll send it to you. Okay, that's saved. Any questions before I go to the next board? Okay. So other examples. Well, you see, the one we just mentioned, the Hopf link, is certainly the simplest classical example you can think of. Two crossings, very nice. But you could also just go back and do everything for a little curl and see what you get. What could be simpler than that? So that's another good example. And then the next culprit in the panoply of things to think about would be the truffle knot. And we know how the truffle knot begins. And there are 8 states. 8 states and more enhanced states. But you could certainly write this out. You could do exactly the chart that I just told you, but do it for the 8 states of the truffle knot. And I will have this all prepared so we could look at it and compare notes if you are interested in doing it next time. If you don't have the time to do it, you will see it worked out in any case next time in the detail. We could get all the states and check that how they were contributing, and we can see the boundary maps and everything, so that after a certain amount of work, we would have the homology and everything for the truffle knot. After that, it starts getting in need of a computer, I'm afraid. If the next simplest knot is the figure 8 knot, and this has 16 states, 16 main states, I would say, and more enhanced states. So by that time, it's getting to be something that would be very exhausting to do by hand, and you might do it if you became fanatic about it. But that's the story for classical things to look at. Are there some other classical situations that we could look at that might be interesting and not too hard? There are. So I want to mention it to you. And then we also want to talk about virtuals, which is what we're going to talk about very shortly in a few minutes. But before virtuals, we have knotoids. And I think we mentioned knotoids before. But I remind you, a knotoid is a knot diagram with ends, and the ends are not necessarily in the same region. and you do Reidemeister moves as usual, but not allowing passage across an end. So in other words, forbidden. Right? And then you have a knot theory. And this includes things like this, which are really equivalent to ordinary knot theory. These are called knot type knotoids. Now, the reason I mention knotoids here is because everything I said about doing Khovanov homology can be done for knotoids. No problem at all. You define the Khovanov complex exactly the same way. Think about it a little bit. Suppose that you were going to take a certain state of this guy. So it might be looking like that, right? Excuse me, I segregate my considerations here. You see? That's what a bracket state of a knotoid would look like. That's the A state of that knotoid. We can go ahead and calculate bracket polynomial for knotoids. I'll do an example in a moment, but I just want to encourage the possibility of doing some examples. Why? Well, of course, because you see, if we do that, then we have more examples because that we can do that are small. This only has two crossings. It's no worse than the Hopf link. You could calculate the Khovanov homology for this just as well. And what are you going to do? You can just use enhanced states for these. So you're going to have a plus or minus on this and a plus or minus on that. And you're going to evaluate everyone. If you did it that way, then you would find that you were evaluating the closed loop as a Q plus Q inverse. And you were also evaluating of the other one as a Q plus Q inverse, just to make life as simple as possible. Or you could decide to evaluate it slightly differently. And I'm not sure what the right grading choice should be there. But I suggest we think of it that way for the time being, and I'll check the grading choices. But you see, you're going to just treat it as though it were a circle, but it isn't. And you're only looking at this material in here, and you make a Khovanov complex in exactly the same way. And you have a Khovanov homology for knotoids. All right. And so you can calculate those as well and try out some examples with them. So let me digress for just another couple of minutes about knotoids, and then we'll come back to the real question, which is, how are we going to do this for virtuals? So let's do the usual bracket polynomial for knotoids. So then we would be expanding in the usual way, like this, A times this plus A inverse times this. And in that one, I'm going to take the convention that if I have a loop next to somebody, it multiplies by the usual loop value. And I'm also going to assume that the value of the little leg is going to be taken equal to 1, and the value of a little loop all by itself is going to be equal to 1 as well. But here, I mean the value of a little leg next to a k is going to be 1 times the value of k. I won't give it any value at all. That's a little bit inconsistent with what I told you to do for Khovanov homology, but it's the most efficient thing for calculating these. This is invariant under Reidemeister 2 and Reidemeister 3, just like the usual bracket. You can investigate that. And you can normalize this in exactly the usual way. Fk of A is equal to minus A cubed to the negative writhe of k times bracket k. And then you can go ahead and calculate bracket polynomials of Knotoids. So for example, if you had this Knotoid and you wanted to calculate its bracket polynomial, it would be A times this one, smoothing it that way, plus A inverse times this one. Yeah. And then we'll expand that, but let's do it separately. We have a little Knotoid link like this, and we'll expand this by the bracket, and we get A. Let's see, there's the A smoothing. A times this character plus A inverse times the other character. Amusing, huh? And that's just A plus A inverse by my reduction rules, keeping everything as simple as possible. So this is A plus A inverse. And then I get that this guy here is going to be equal to A times A plus A inverse plus A inverse multiplied by, that's a negative curl. Have you gotten to the point of being able to recognize a negative curl when you see one? You just in your mind's eye orient it and check that this is a negative crossing. So, excuse me. I just got lost. A inverse times, oh, I'm up here. That's right. Yes. A times A plus A inverse times negative curl minus A to the minus 3 times little long, which is 1. And so this adds up to A squared plus 1 minus A to the minus 4. And then if you were to orient this, you see that those are both positive crossings. So then the Fk, if this is K, the Fk is equal to minus A cubed to the negative writhe, negative sum of crossings, which is negative 2 times the bracket, which means then I'm going to multiply by A to the minus 6. So I get A to the minus 4 plus A to the minus 6 minus A to the minus 10. And that implies that K is not equivalent to its mirror image and non-trivial. Okay, so that's the initial simplest bracket calculation for this Knotoid, proving that the simplest Knotoid, which has only 2 crossings, not 3, is a non-trivial Knotoid and inequivalent to its mirror image. And so the subject of bracket polynomial and possible Khovanov homology of these things extends to Knotoids and is certainly something that needs to be investigated. It hasn't been investigated very much yet. And we have a conjecture, just like the one for the Jones polynomial. Oh, wait. All right, we'll save that as it is. The conjecture is that bracket K detects the unknotoid. Okay. In other words, if you should find a knotoid, and you know, there are lots of them, just like there are lots of knots, piles of knotoids. If you should find a knotoid, K, and this was equal to some plus or minus power of A, then the conjecture implies that K is equivalent to the unknotoid, just like the conjecture for the Jones polynomial. Of course, we can't prove this. We don't know how to prove this, but it might be true. And it also might be true that the Khovanov homology for knotoids might detect the unknotoid. Of course, that might be easier. It's known for classical knots and Khovanov homology via the work of Kromheimer and Moravka. Their work involves something that would be very interesting for us to look at. If we wanted to sometime, instead of listening to me talk, spend an hour listening to a very good the video of Kronheimer talking, or perhaps I should just send you a recommendation to listen to it. You can hear their gauge about their gauge theoretic techniques that allowed them to prove that Khovanov homology does detect the unknot. So while we don't know if the Jones polynomial detects the unknot, we do know that Khovanov homology detects the unknot by gauge theoretic methods. And it could be that the gauge theoretic methods can be transferred to knotoids, in which case it might be possible to get a proof that Khovanov homology for knotoids detects the unknotoid. And to prove it at the combinatorial level of the polynomial may be very, very hard. So in any case, knotoids start with very simple examples, and that's one of the reasons I'm mentioning them, because if you want to get a feel for something, small calculations are helpful. But now let's turn to the question of virtuals. Interesting question. Yeah. What are we going to do about that? Well, there's a problem. It's easy to explain this problem in a nutshell. Look at this. Here's a virtual crossing, and here's a smoothing state, an A. And I want to take a category arrow and go to a B. So I do. But this has one component, and this has one component. It's a single cycle resmoothing. Now, we might mention, as you may have noticed, that this has the feel of something non-orientable, because in fact it is a non-orientable saddle point that you went through when you did this. Notice what happened here. If you oriented it to think about going through a saddle point, then this would be going that away, and this is going that away. And so when you reorient it, it's not when you went through the saddle, you don't have a natural reorientation. Natural inheritance of an orientation here. It's a non-orientable saddle point. So of course, if we're going to think in terms of cobordisms, we should take that into account. But let's just see what we can do. So suppose that we decide to call the mapping that this would be eta. So there should be an algebra mapping eta. If A is equal to our Frobenius algebra, let's say it's K of X mod X squared, etc., same as before, the Khovanov algebra. Then we're going to have a mapping eta from the algebra to the algebra, just like we have a mapping M from the algebra across the algebra into the algebra, or algebra tensor, the algebra, the multiplication, and we have the coproduct, which takes the algebra into the algebra tensor, the algebra, and we should have this eta. And then we're going to assume now, although later we might try different possibilities, assume now that eta is 0. Now, I have a feeling I told you this story before, but now we're looking at it seriously, so let's take care. I'm going to take eta equal to 0, and I'm going to then want to see whether I could work the way I worked before and continue to make the Khovanov complex. So let's look. Here's an example, very simple example, not a very interesting complex, but a good example nonetheless. So this is the knot diagram that I have in mind in back of things. And so I'm going to have, I think I wanted it the other way. Yeah. It really won't matter that much. Oh, I guess it does. Let's see. My favorite example. thought that's the way I wanted it. Let's see. If I smooth this one, I will get a loop. If I smooth this one, I won't. I think I'm inclined. It's just I'm used to drawing an example. All right, so we'll do that. And then this will be the A smoothing, and this will be the A smoothing here. Still a trivial length. But let's consider this. And this is the first A, and this is the second A. And if I go this way, this is a virtual crossing. So we're looking at that example. And we're going to go like this. And now I'm going to smooth this one. And again, it's an eta. All right. So here's an eta and here's an eta. And if I go around the other way, then I'm going to smooth this one first. And then I go here. So this time I'm doing a B here, and then I'm doing this B. So the first time I did this one, and that's a coproduct. And then I'm doing this one, and that's a multiplication. So there's the square that I'm interested in. And you see immediately that if I take eta to be equal to 0, then eta composed with eta will be 0. So this map will be 0. And what will we get here? Well, we'll get M composed with delta. Well, what is M composed with delta going to do? Let's suppose we had a 1 here. M composed with delta of 1 is equal to M of 1 tensor x plus x tensor 1. And that's equal to x plus x, which is equal to 2x. I'll do another one. M composed with delta of x is equal to M of x tensor x, and that's equal to x squared, which is equal to 0. That's okay, that's 0, but this one, that won't do. I haven't got a commutative square. I need a commutative square or an anti-commutative square, but a non-zero square won't do, right? It won't do to have this 0 and this non-zero, just won't do at all. On the other hand, mod 2, it's okay. So the fact is that Khovanov homology is okay mod 2 for virtuals. So that's something of a relief. That tells you that you have the mod 2 theory, and you can explore that for virtual knots, and you don't have to change anything. Of course, you have to investigate a little further to convince yourself of that, but this is the key difficulty, and there's no difficulty. So modulo 2, everything is fine. But we would like to do it integrally, and that's what we want to talk about now. But in terms of doing examples, now you're home free for doing examples. Mod 2 examples, right? Well, let's think about that for a moment on this slide. So you might want to play, right? So just put that here. Everything's okay, mod 2. So now, now you have more examples. For example, you have the virtual trefoil knot, and that has only 2 crossings. So that Khovanov complex will be produced by you just as easily as the Hopf link, and I recommend it. And that's more homework for next week, but we'll go over in more detail next week. But there's a nice example. You should do it, mod 2. Even simpler than that would be this one, where it's only got 1 crossing, and anyone can write down the Khovanov complex for that, mod 2, and see how it works. And there are a few more because, it starts out with fewer numbers of crossings. So that's a good deal. And now let's try to think about what we could do to understand what's going on and change the rules, because we will have to change the rules somehow in order to get a complex that would work over the integers. And the way of changing the rules that I'm about to tell you about, and it will, of course, go on into next time, but there's enough time now to begin, is due to Vasily Montourov. So, let's keep this box. Oops. Sorry. There's a hint involved in that virtual crossing. And so you might have the following idea, which is something like the idea behind Vasily's method, but we'll get to the correct formalization of things in a little bit. But you might think, well, maybe wandering through a virtual crossing has something to do with this. If I could somehow get a sign to appear that would cancel one x tensor. Remember, we were going one tensor x plus x tensor 1, and then we were going x plus x equals 2x. That's how we did it. And then, of course, we're going this way, and this was eta squared. But the problem was here, and maybe you could get this changed to a minus. By counting something. Well, you could count whether you went through a virtual crossing or not. And so that's the idea. We're going to use local coefficients so the algebra has location on the diagram. And then I'm going to try, which turns out to be wrong, but it's a nice try, so it's worth showing it to you. I'm going to try that if I have a bit of algebra here, A, and I push it through a virtual crossing, I will change the algebra to some A bar. I won't worry about what it is, but it should be an involution, right? A bar bar should be equal to A, so that it's just a parity matter, and then it won't matter, how many times it happens, or if I had something that doubled back, and so on. So that's an idea. And now let's see what that idea would look like. I might start here with a 1, locally here a 1, at the site where I'm going to do my coproduct. So then I would end up with a 1 and an x, or an x and a 1. Let me maybe, no, I won't go coloring everything up, but this means x tensor 1 plus 1 tensor x, all right? But this algebra is localized to this site. Okay? And now, in order to do the next operation, which was to multiply, this funny feeling that I'm at the wrong site. Am I at the wrong site? I am, because the one that went down was this one. So sorry. Let's do it again. Wasn't watching where I was located. If I'm going on this one, then this is where the algebra is located, right here, and this is where I did this, right? So I have my algebra located here, and I do coproduct, turns into circle and circle. So you can think of the 1 as locally splitting into a 1 on that circle and an x on the outer circle, or an x on the inner circle and a 1 on the outer circle, okay? And now we want to transport this algebra up to here, which is where the multiplication occurs. So now I'm going to use a little color. So I'm going to transport this x up to here. And I'm going to transport the 1 up to here as well. And neither of those transports goes through a virtual crossing. I'm going to transport this x, however, through the virtual crossing, and it ends up here, or over here, really, because it should be paired with that one. And this 1 will also be going through the virtual crossing. Pardon me, it goes crossing over, but it goes through the virtual crossing, and it ends up over here with the 1. So, sorry. We'll just write those arrows and abbreviate them a little bit. So what we get is x comes up here and a 1 comes up here, but it got a bar in it because it went through a virtual crossing. And the other one, the other x also traveled and it got a bar on it, right? So you see that we are now about to multiply 1 bar tensor x plus x bar tensor 1 to get here. By counting the transport of these elements through virtual crossings, we found out this. And now you see that we could try x bar equals minus x, and 1 bar equals 1. A kind of conjugation operation. And then this will give us what? Let me erase this bit. This will give us 1 bar. Oops. This will give us 1 bar times x plus x bar times 1, which will be equal to 1 times x minus x times 1, which will give us 0. See, it introduced the sign in the way that we were hoping it would. So that's an idea, right? That we will make the algebra local coefficients on these little spaces that are the states. And when we do an operation like multiplication or co-multiplication, then we will keep track of the algebra and where it ends up. And then we will move that algebra over to the other site where we do the next operation, and we will apply the involutions to it as it goes through virtual crossings. And then the signs appear to be working correctly. It's a good idea, except it's a little bit wrong. It isn't really the right thing to do, or at least we don't know a good way to do it by just counting virtual crossings. But we can count something which is very closely related to virtual crossings. And I'm going to show you what that is. And perhaps that's where we stop, and we'll continue explaining how this works next time. But the thing that is very important to understand is a notion of reorientation that we're going to use. Go back to a classical knot diagram for a moment. And now I claim that in a classical knot diagram, you can always compatibly orient this in the following way: 2 out and 2 in. I call that a source sink orientation. And I claim you can always do this on a classical diagram. You might just try it. Let's try it on the trefoil. 2 out and 2 in. And then I want it to be compatible. So that means I back up here and this one would be out. And I back up here and this one would be out. And I back up here and this would be in. So this must be in and that must be out and that would be in. And then that would be in, but that's okay. And this would be out and that's okay. And as you see, it works, right? You can always decorate a classical diagram with a source sink orientation. Exercise. Okay, but now it's a nice exercise. You should do it. But what happens if you had a virtual knot diagram? Oh, I'm sorry, I'm drawing in some profligate manner. Here's a typical virtual knot diagram. Now I do this, I try this out. Okay, so I say, let's have these out and let's have these in. Now, presumably with a virtual crossing, If it's going along, it continues along. If it's going along, it continues along, right? There is no other orientation for the virtual crossing other than just continuing on through, because it isn't there, right? It's just as though these two lines were separate from one another. So that means that if this is going to be a virtual crossing, then this arrow goes right through it and comes over to here, right? But then that's going in, so this should be going in, this should be going out, and this should be going out, and that determines what happens there. But now we're in trouble, right? We're in trouble. We have this cut point where the orientations don't work, and we have this cut point where the orientations don't work. So it turns out that we can measure involutions across cut points. So instead of counting virtual crossings, we count passages through cut points. And then we can systematize exactly where the cut points are and make this scheme, which I told you about, actually work. And let me give you a quick tour of what that looks like. And then when we start again next time, we will have a lot of interesting things to do, various examples, and more information about how this is going to work out into a definition. So I have a little slide. I have a couple of slides for presenting what I was just telling you, and we can look at them a little bit. I'm going to go perhaps a little too quickly through this, and we just have a couple of minutes left, or we don't have any time left, but let me just show you what it looks like so you see it systematically. Here's my Frobenius algebra. Here's my involution, minus x for x, and 1 bar is 1. And then you can see that the involution behaves somewhat like complex numbers. The bar of a product is the product of the bars, and z bar w bar is z, the bar w bar, and you can check how it behaves under coproduct, and you can check how it behaves under product. So there's some algebra there. And then we're going to have, instead of using a crossing like this, we're going to replace it by a source sink orientation. And then we'll do that in a standard way. And then we also have to keep track of the order of the cycles that we make when we smooth them, but we'll come to that later. And then we count with regard to cut points. So we might have a situation like this with some cut points, and then we have to keep track of the orientations, the orders of cycles as well. And that changes, that also creates minus signs if the orders have to be switched. And after we do all that, we end up back at the exact exercise that I was showing you before. And now the exercise will give us anti-commutation as we go around a square. In the case of this one, of course, it just gives us 0. The signs work out and it vanishes. But in the case of other examples like this one, we find that it anti-commutes. And so by setting up these new signs and an order convention, we can make all the squares anti-commute. And they anti-commute in a somewhat different way than they did in the regular Khovanov homology, but in such a way that when we restrict to ordinary classical links, it gives the same results. And it extends integrally to give a Khovanov homology for virtual links. So this is the Vasily Montourov solution, slightly modified by myself and Heather Dye and Aaron Kastner with the involution brought forward. But it's a very clever idea that manages to work and deserves further investigation. And we have been able to use it, just the existence of the homology, to use it to get some results. And I'll be talking about that. So this is the nitty gritty now, with lots of different things, lots of different exercises that are good to look at. And I'll stop there and we'll continue next time.
Thank you very much.
Thank you. Thank you.
Questions? No questions?
So I have one small question, if possible. So if you think about virtual nodes, you can define bracket polynomial, and you can work with this polynomial. And if you have Knotoid, you can consider the closure and reach to virtual node, or you can define the bracket polynomial for Knotoids.
Yes. Mm-hmm.
It will be the same polynomial or different?
I'm sorry, I didn't get the question.
Oops. Can you hear me?
Yeah, I hear you fine. I'm not quite sure what your question was. Was it we can define the bracket polynomial for the Knotoids?
Okay,
yes.
so I will try to repeat. So let us think about bracket polynomials. So you can define bracket polynomials for virtual node.
Mm-hmm.
Okay. At the same time, you can define bracket polynomial for Knotoid.
Yes.
And if there a standard way to go from Knotoid to virtual node, which is a closure.
Yes, that's right. I wasn't mentioning it, but yes, that's right. And then you will notice that if you can define a bracket polynomial for a Knotoid by just taking the virtual closure and taking the bracket polynomial of the virtual closure.
So the result will be the same. So you get the same.
And the way I defined it by taking if I had defined it so that the long state acted as a loop, minus a squared minus a to the minus 2, then it would be the same. I think I've abbreviated it by knocking that out, so it won't be quite the same. Almost the same.
Okay, thank you.
Yeah.